Okay, cool. So today I'm going to be sharing about machine learning in healthcare. It's a very specific aspect of machine learning in healthcare. What we try to do is to try to build a cost prediction system for Southeast Asia's largest hospital group. So let's just jump into that. So this is what we built. We launched it a while ago. It's a estimation system. So I mean, we call it AI powered predictive, whatever. But this system, since then, we have been able to put it online. It's consistent uptime. It's reliable enough for them to start providing fixed costs surgical procedures for some procedures. So in the sense that we're able to just use this and just provide fixed cost procedures. So why is hospitalization cost prediction important? So I think in Southeast Asia, this is where Singapore is. It's one of the most expensive in Southeast Asia. Of course, can't compare to the United States, which is all the way up here. And you know, Singapore is very, very high on medical inflation. It's 10% in 2019. And the biggest cause of it, the biggest uncertainty part of it is hospitalization for our patients. So that is what these hospitals are trying to provide patients with a bit more certainty on. They want to provide them with upfront cost estimates so that we can improve the patient's experience and also retention. So what we found is that, hey, you know, when providers provide upfront cost estimates, it's easier to attract the patients because they have a bit more certainty. It's not a guarantee, but they have a bit more certainty on what the procedure or what the treatment is going to cost them. And you can see the citation is here. Oh, sorry. And of course, for the patients, providing them a view of the potential bill reduces payment challenges with providers. What this means is that, hey, someone might want to come to get a specific surgery, but if they don't know how much it's going to cost, it might cost a lot more than they expect to, and they might just go ahead with the surgical procedure without knowing cost. And what happens is that at the end, they are not able to pay for it. So this is not good for patients, as well as it's not good for providers because they are out of the pocket. The doctor's time has been spent, the surgical procedure, the operating room has been rented, and all the materials have been used, but no one's going to pay for it. So let's start with the problem. The problem is, or rather, let's start with the intent. The intent is to provide patients with more accurate estimates. So they currently do have estimates, but they want to make it more accurate. So there's a key business requirement, which is for the model to overestimate instead of underestimate. So let's try to think about this. So imagine your bill comes and it's $10,000, and it differs from the predicted cost by $5,000. Okay. It could be that your prediction is $5,000 and now you have to pay $5,000 more. On the other hand, it could be that your prediction is $15,000 and you pay $5,000 less. For each of this, to the machine learning model, the error is the same. So the machine learning model doesn't know which is better. But we know from the business domain that they prefer to overestimate in order to have a better customer experience. Because if you overestimate, the customer walks away happy, right? The patient walks away happy. Of course, this needs to be balanced. We don't want to provide bills that are too high because when patients are looking for procedures, they might be shopping around and they might not, if you provide an estimate that's too high compared to your competitors, they might not even come in for the surgical procedure. But by and large, there's a preference for overestimation. And of course, we have a key constraint, which is that they already have existing estimates. They already have existing UI that their nursing staff, their hospital staff is already using. So trying to build an entire system to change this is really expensive. You need to train all the hospitals, you need to train all the nursing staff, you need to train all the people. It's really, really difficult. So our key constraint is that whatever we build must be plug and play into their existing UI. So you can see here, we have two key requirements. One is to, of course, clearly we have to be more accurate. Second is to overestimate. And third, we have to do minimal disruption. So given our intent here, let's see how we design a system that meets this problem. Any questions so far? No.
I do have one. So I'm
Yes.
wondering, So why it's not clear what the cost is upfront? Like, why is this a problem in the first place?
This is a good question. So if it's when people come in for surgeries, if it's a very standard surgery, it will be very clear what the cost is upfront. But sometimes people come in for surgeries, and we can itemize all the item costs of all the materials and the doctor's time. But sometimes there might be complications, or all the best we can provide is, people go through this surgery, they're gonna stay in the hospital for 3 days. But some people might have existing pre-complications, that there might be comorbidities, so they might have to stay longer. A lot of this is difficult to estimate upfront. However, with certain demographic variables like age and gender, it is easier. But you're right, this shouldn't be a problem, but it is.
Okay, I understand. So basically, if there is a complication, then
Yeah.
extra work is required, and then it increases the cost
And they have
afterwards.
to stay longer in the hospital, which is quite
Okay,
a significant cost as well.
understood. Thank you.
Okay, thank you for that. So now, what is the problem? The problem is that the existing system has very poor accuracy. So it's a very basic system that uses statistical aggregates, and thus it cannot capture the nuances of each individual patient. It just sort of aggregates all the surgical procedures across a certain amount of time, and it doesn't personalize the estimate. And because of this, they found it very expensive to update the models, because it was fully within their control. Every time they update the model, they had to run it through hospital administrators, medical staff, including doctors. So you can imagine the time taken to update this model itself was really expensive, because you're using the time of hospital administrators and medical staff. As a result, this model was updated very infrequently. And when models updated very infrequently, it leads to poor accuracy. So it's a vicious cycle. So how do we try to solve this problem? So I have a slide here that takes us through the high level. Let's have a big picture view of it. First of all, no need to take screenshots, because all these slides will be completely available. So I hope you can see my mouse pointer, but over here, this dotted gray line, this represents the delineation between their environment and our environment. So the hospital environment, the hospital has data on the patient, doctor, and the case, etc. So periodically, they would extract the data, could be in CSV format or whatever format, and encrypt it via the cipher that we provide. And from their encryption server, they will pass it to us on our decryption server. So on our decryption server, we would again decrypt it, and then we don't do anything. We just put everything in the staging block. That way we have the raw data as how they have provided. Of course, the encryption has to match, and so we know that we have the raw data. Once we have the raw data, so this is usually something in S3 or Azure blob. In this case, we're using Azure. After we have the data, we do very minimal transformation to make sure that it can sit into our relational database. In this case, is Postgres. So essentially taking CSVs, doing minimal preparation, not cleaning anything, putting in the data storage. So this is our raw data store. After that, we go into the data preparation, feature engineering, machine learning, etc. So all these steps, I'll go into greater detail later. So the outcome of this, what we do here is that we train a model. Of course, we do all the necessary data prep and feature engineering. So we train a model, and this gets stored in a ML model storage. So the form of these models, it could be anything. It could be pickle files, it could be PyTorch storage format, or Docker images. I personally prefer to wrap the model in a Docker image, so with the serving code and everything. So that way we know that we can just take the Docker image, run it, and it will be plug and playable. So this model storage, and we'll see why we need to store models later. So after we have the model storage, it goes to a publishing server. So what the publishing server does is that it takes the model, and again, it stores it in an artifact storage. So this would be something like Docker registry, Elastic Container Registry. And then it takes that, keeps a copy of that. Oh, so why do we need a publishing server? It could be the case that your ML model storage is not in Docker format, right? Or not in a way that's ready to serve. So the publishing server would do that and put it in a ready to serve format. And then we deploy it. So when we deploy it, each hospital has their own API. So we deploy to the different APIs, and all this is served via API server. There's a thin layer of business logic. For example, maybe hospital administrators want to have a minimum price for certain procedures, or they want certain procedures not to go beyond a certain price, whatever. They can add that. And all this is used by the hospital staff as well as the general public if they have access to the website to call their estimates. So they will enter things like my age, my gender, what my surgical procedure is going to be, what my existing what my existing conditions are, what procedures I might have done in the past, etc. So they will get estimates here, and again, these estimates get pumped back into the estimate database on their side. So this completes our feedback loop. And over here at the bottom, you can see that this whole thing, we orchestrate, this whole thing, we monitor it via the Elasticsearch, Logstash, and Kibana stack. So all this, we have logs that just get pumped into Logstash and can visualize it with Kibana. Over here on the top, how we orchestrate this is through Airflow. It's pretty standard. Airflow is pretty basic. It's a de facto and it's easy to use. And over here, the publishing server, we use Jenkins. And so you will see that this is built on top of Python. So most of it is Python, PySpark deployment as well. I think our API server might use Node.js, but I forgot the details. And this is done all on Azure. So why it's done on Azure? Because most of the healthcare clients are on Azure, and that's what they're comfortable with. So any questions here?
Yeah, I do have one. So like there is this difference between Airflow and Jenkins. So I'm just wondering, why do you need to have two systems? Like what do you do with Jenkins that you cannot do with Airflow?
That's a good question that I am not able to answer.
Okay.
So the DevOps, to be honest, this part I'm not. I don't claim this part is not done by me. This part is all done by the DevOps team.
Okay.
So they use the Jenkins for deployment.
Clear. So basically, the tool that the team was comfortable with was Jenkins rather than Airflow.
Yeah, we use Airflow, but I think there's a step in the middle that they felt that they needed to use Jenkins. Yeah. Okay, so moving on. So this is the big picture view, and now I'm going to dive deeper into these steps. More of the focus here, but yeah. This is just a quick view of how this would be organized in code. You can see we are now on version 3. We would have, and this is like the source directory. We have data prep package, feature engineering package, machine learning package, and utility package. And of course, we have our tests, which mimic the exact package. So specifically under machine learning, we have several packages. One is the train package, which trains the model. Next is the validation package, which validates the model before we can serve it. And then there's a serving package. In the serving package, all this does is there's an API, which is essentially just a model class that contains your state. And then there's a package API, which takes our model and package it into the API. That's it. Data validation and ingestion. So you can see that I mentioned that the data comes from the provider environment, and they encrypt it, comes to us, we decrypt it, and we do data validation. So I think this is pretty straightforward, but I think it's useful to chat a bit. So initially, the data was provided via ad hoc SQL queries, and sometimes these SQL queries might not match. So as a result, the schema and field formats might differ. So for example, the data format might switch between UTF-8, Latin ISO, ASCII, and Python. And machines are very sensitive to such formats. It will break. So we have to check the format first. And sometimes we also want to check the columns, right? Whether the columns are the same name or not. So if the column is a missing name and we just continue to ingest the data, we could ingest the data correctly, and we have the entire column full of null values, which is not what we want. Second, we also want to check for duplicate data. So duplicate data is actually very dangerous. Why is this so? So for example, maybe they provide us data week on week, but the data that they're supposed to provide for last week also contains the previous week's data. So in this case, the previous week's data would be duplicated, and we might never know. And now this is in our raw data store, and to clean it up from the raw data store is very, very difficult. Once the data is in, unless you allow delete operations, it's going to be very difficult. So we want to check that whatever data that we ingest is no duplicate, no null values. And the last one is volume checks. So for example, maybe you might expect that the periodic volume of the data is about, I don't know, let's say 10 gigabytes. And we know that it should be fairly consistent week on week. However, if the volume of the data on disk is, I don't know, more fluctuates by more than 20%, that is something that we might want to warn ourselves against. For example, you could meet everything, right schema, right column and everything, but your entire data set is full of empty string, and you would still pass. So we also want to check the volume. So after we have done the data validation, and this is on the raw data that is still in our, could be in the CSV format or Parquet format. Only after this is done, then we extract it, load it, and transform it into our raw Postgres relational database. So now this is the raw data store that we are going to be using. From this raw data store, we do some data preparation. So this data preparation is very basic. Nothing too fancy here, but I thought maybe we can talk a bit more about this, some stuff that's specific to healthcare in general. So categoricals, so ICD-9, ICD-10. What is this? So this is the International Classification of Diseases, and right now we are on ICD-11. So we might have different cases where the ICD is different, and to a machine learning model, if you use male as in MALE versus M versus boy, the machine learning model is going to see this all as different, but we know that they're all the same. So we need to normalize this. And of course, standardization in terms of gender and the hospital room types. Numerics. So we want to fill in missing values. So filling in missing values is nothing too special. You can do this by filling in with your mean, your median, or using a special value like -1 to represent missing values. Handling outliers, a very interesting case. So healthcare costs, hospitalization costs is very much right skewed. Is that you're going to have quite a lot of people which have average costs, and there's going to be a long tail of people with outsized hospitalization costs. So are those outliers in our data set? I don't think so, but we want to handle them properly. I think I want to mention here that if any of you, if we are taking the steps of handling outliers in our data, I highly recommend handling outliers in your training data so that your model can at least train properly, but try to leave them in your testing data so that at least your testing data set, the distribution, matches your actual production data set distribution. So that way, you can't say that, hey, in the testing data set, the root mean square error is very low, but why is it so high in production? It's because you remove all the outliers in your testing data set. So it gives you a better sense of how. And of course, we might have other stuff like text, doctor's notes or images, etc. Those have their own handling as well, which I will not go into here. So now that we have patient data, doctor data, case data, etc., whatever, we need to merge across them to generate a single object, a single entity. And the entity here is a case. So a patient can have multiple cases. A doctor will definitely have multiple cases. So we train our model on the cases. And after that, we could do data augmentation. So what does this mean? We might have external data from doctor data from the Singapore Medical Council, SMC. So all this data is available on the website. It tells you how long the doctor has been practicing, what's their specialty, etc. So all this can be useful as well. We also have our own internal features. For example, we've seen a lot of such data, a lot of such diseases, how disease progress across time, and we develop our own disease embeddings that we can merge in. And so this is how we augment the data. Alexia, any questions here?
No.
Okay, cool. Then I'll go into validation. So this part is really, really important. I think this is the most important slide of the entire deck. I think that in almost all machine learning cases where your model is deployed into production, you should never use a random train test split. So a random train test split, we know this is five-fold cross validation. We just split into 5 and we shuffle data and we validate accordingly. So the other way is the time-based split, whereby, this is my year 2016, I predict hospital bills for year 2017, 2016 and 2017, predict hospital bills for 2018, 2016 to 2018, predict hospital bills for 2019. I think that most of the time we should only do this. We train only on data from the periods before. And let me share with you an example of how this matters in our specific use case. If we use a cross-validation split like this, we might use, given probability, we will use the future data to predict past data, and the validation results will differ greatly. So what we found is that 19% of our patients had more than one admission. So this is close to 2/5 of the hospital cases that we have. So what this means is that we could take a patient's future admission data when we're doing a train validation split, a future data to predict the past data. And that would never happen in production, right? And also what we found that in validation, when we use a validation across time, we would have a lot of cases, more than 100 cases where the specific ICD-10, International Classification of Diseases, so the specific diseases or the specific table of surgical procedure, the specific surgery has never been seen before. So clearly, again, that when the model doesn't see anything, it hasn't seen it before, it will not know what kind of embedding or what to use. However, when you do a cross-validation split, you might have that data. So again, it's looking backwards in time. And lastly, we know that medical prices increase over time. So let's say I have 2016, 2017, 2018, and I'm trying to predict 2019, but I also have 2020 data. If I have this, all I need to do is to draw a line between 2018 prices and 2020 prices and just sort of guess what's in the middle. So this is a lot easier than just trying to predict what happens in future. So in our case here, using a time-based validation is very important. So nonetheless, there are some cases where it's okay to use a random split. So for example, I'm just going to take a basic example, product classification. I'm classifying products based on title, based on images. So the distribution of this and their product actual classification doesn't change that much across time. So in this case, it could make sense to use a random tree-net split. For example, ImageNet, the images and what they are probably won't change across time, right? A dog will still look like a dog. A hamburger will still look like a hamburger. Maybe in 10, 20 years, it might change a lot, but for now, for the next 1 to 2 years, it'd be pretty constant. So that's where a random train test split would work. Feature engineering. So again, we use very, very basic feature engineering. Grouping. So the diseases and the surgical procedures, they have a hierarchy, right? For example, maybe at the top, you have a cough, and then you have a pneumonia or dry cough or wet cough, and another pneumonia, you have different. So one basic way is to just group it to a higher level. Why this is helpful? Because there could be some very rare instances of diseases or surgical procedures that are seldom seen. And by grouping it together, we actually, the model is able to learn it better. And of course, encoding it, it's up to you how you want to do it. You can do one-hot encoding, binary encoding, numerical encoding. I mean, I won't go into too much detail here. Or right now, what most people do is, just create embeddings for these. Numerics. So let's say we have our numbers, we want to normalize and bin them. So one important thing is that, again, hospital data is very much right skewed. So it doesn't have a normal distribution. So one way to fix this is to create statistical transforms. For example, the most standard one that works very well is to use a log transform. You just log all the values and it becomes somewhat of a normal curve. In our data, we have very interesting data on date time. So what this means is that we have time differences such as age, and we have details. So details is a very interesting aspect in our data that we found. For example, imagine someone trying to get an estimate on a Wednesday afternoon. Okay, someone trying to get an estimate on Wednesday afternoon, and then imagine someone else, the same person trying to get an estimate on a Saturday night at 2 a.m. Which of these is going to be a more serious case? Clearly, the one that's on Saturday night at 2 a.m. when they come in a hospital and the nurse is there trying to get an estimate, that is clearly a more serious case. So while we may not know the extent, the severity of the case, because this is before the nurse has entered in triaging or the doctor. But one interesting instance we found is that the time of day matters a lot in terms of how serious it is. So that's something to think about. Lastly, we have interactions. So interactions is essentially just cross features. You cross your age and gender features or your age and surgery features, and they become a new feature. So age and gender basically a male and whatever age and surgery. Certain surgeries are, in general, surgeries are not so. The older you are, the less well a surgery is going to go. However, for certain surgeries, this matters more. So if you cross these features, you can also see a lot of things. And of course, conditional probabilities. Essentially, it's just a grouping, and then you calculate a conditional probability or the conditional, or you get aggregate costs, and you use that as a feature as well. Any questions here so far?
Yeah, I'm just wanted to. I think I understood why the time of day is important. Just wanted to double check. So basically, like, if it's not serious, you wouldn't go at night. You would just spend night at home and then show up in the hospital the next day, right?
Exactly. You wouldn't be there at 2, 3 a.m. Usually the cases that are there at 2, 3 a.m. are emergency cases.
Mm-hmm. Okay,
Yeah,
makes sense.
Machine learning. All right. So I don't know what the level of the audience is, but when I was preparing this, the level of the audience was pretty basic, and to them, machine learning was a black box. However, machine learning is not a black box. As you and I know, it's actually pretty basic. We have models and objective functions. So over here, we have different models. I'm just going to list the standard ones: k-nearest neighbors, logistic regression, decision trees, neural networks, regression neural networks. And in our case, we're predicting a number. So we have different objective functions like mean squared error, mean absolute error. However, one thing is that the mean absolute error, the second order derivative is not curved. So we might have to use other things like Huber and Fair. Feature selection. Again, you can just use classic feature importance. However, one thing to note here is that classic feature importance doesn't really work correctly. So what do I mean by this? So imagine that you are trying to predict the likelihood of breast cancer in patients, and you only have two features. You have age and you have gender. So let me ask you this, Alexei. What is the first feature that the model was split on in predicting breast cancer?
Gender?
Yes, gender, right? Because everything that is male will not have breast cancer. And then everything that's female has, and then after that, it will split on age multiple times, right? To cut it. From the model's perspective, because it splits on gender only once and splits on age many times, age is a more important feature. If you use regular decision trees, you do dot feature importance, that's what you could get. But we know that gender is actually the more important feature. But the way that classical feature importance is calculated, this does not come out. So we might want to consider permutation feature importance or drop column feature importance. Now, data weightage. This is a very, very interesting topic, at least in our use case. One interesting thing that we tried is to weigh the data by time, because we know that the older the data is, the less relevant it is. So we tried to decay it linearly or exponentially. And of course, we have domain knowledge on how to weigh the data correctly, weigh the data properly. So for example, while working with our clients, the hospital administrators, they told us, that this data is more important, that data is not less important. They told us to exclude certain data, which is wrong, which is completely new to me. I always thought that more data is better, but they actually told us to exclude certain data that was teaching the model the wrong thing. So that's what we do here. And of course, parameter tuning, again, the fairly standard set of tools, random or grid search, or Bayesian optimization. So that's all we use in machine learning. Deploying it. So you can see over here in the middle, we have a train, validate, and deploy loop. So train, validate, deploy, all this part is very much within our control. we can say that when we deploy a model, we know what the validation score is. So this part is pretty straightforward. However, after that, we get feedback, which is the feedback that we get is the future errors between the estimation and the estimate. So once we get the feedback, we can again optimize our model and retrain it. And so you see previously we have this model server. We have a server that stores all our models and all artifacts. So what this means is that let's say every week or every month, we are training a new model. Let's say we deploy the model and we can just give a standard deployment. If you pass the validation test, you just go to deploy it. But it could be that there's a model that passes the validation test, but actually it's not what the customer wants. Anecdotally, they might say that this model performs worse, though it has never happened. We want to have the ability to version or rollback. So anytime we say, hey, this model is a bit iffy, can we roll back? Boom, just take the last Docker image, deploy it, that's it. It's 2 minutes of an engineer's time to do that, and no one needs to work over the weekend, no one needs to stay up late, right? This is your insurance policy. Of course, I know that I've made this look very simple, but this is only the steps that I can talk about. There's a lot of complexity behind here that the rest of the team was working on. So this is by no means a one-man show. They had to take care of the infra, how to get our cloud to talk to their cloud, the security, the encryption, the networking, how to get them to be able to call API via an express network so that they get the best latency performance, and modeling and monitoring, which I didn't cover. So all this, we try to just hide it away from them, and we provide them an API. So the API, let's just say, for example, is JSON based. They provide us the demographics of the patient, some information about the case, maybe the surgical procedure, the disease that they have, and maybe what kind of hospital room they're going to stay in, who the doctor is. Different doctors charge different prices, and we try to predict this. So all this is what goes on in our environment, and all this is abstracted to them via in their environment, and they can just plug and play it into their existing UI. So there's a few things that I didn't cover in the previous slides, but I think it's really, really, really important. I think it's really important to take time to learn from the domain experts and users. For example, they may have certain assumptions, they may have certain human intuition about patients coming in, especially if they have multiple conditions or multiple surgical procedures that are not always visible in the data if you're just looking at data. So what we did was I went to each of the hospital, I just sat down with them, seeing while they use the tool. And then sometimes I would see things that are not tracked in the data, and I ask them, why do you do that? Why do you think that way? And based on this, we can create better features, or at least put some safeguards, right? So this is really, really important. And this is the one thing that made our models a lot better, far better than parameter tuning or feature engineering, which is trying to understand the problem and how they're going to use it. Second big takeaway is more data is not equal to more features. So here's a very clear example. We have data from many, many hospitals. So my initial approach was to, just take all the data from all these hospitals and just create a big model, right? You would think that, with a hospital variable, the model should be able to learn all that. However, it doesn't. It doesn't work that way. So different hospitals have different price points. Some hospitals are the 5-star hotels equivalent. Some hospitals are the regular suburb hospitals where they don't charge so much. And different hospitals have different specializations. Some hospitals specialize in enrichment disease, for example, heart attacks, or stent removals, or cosmetic surgery. Some hospitals specialize in the regular accidents like fractures or certain things. So different hospitals work very differently. And by training a single model for each hospital, we found that it works much better. So again, that's an example where more data is not equal to a better model. And lastly, better engineering practices makes everyone's life easier. I hope I've made it clear through this, through the talk of the slide, like having different proper directories, having test cases, having proper versioning, not just code versioning, but model versioning that allows you to roll back, having proper orchestration and logging. It just makes life easier for everyone. Overall outcomes, essentially we reduce error by 50 to 60%. We reduce the amount of underestimation. We improve the query latency. I think this is actually like 40 or 60 milliseconds. Previously, it used to take them 5 seconds because each new query was actually a SQL call. And we allow it to customize it at the hospital level. So previously, their model was a one-size-fits-all for all hospitals, but now because we build it for each hospital, it's better. It performs much better, and each hospital can tweak it according to their desire. Integration of business logic. So we added a tiny business logic layer. So this could be that, hey, they want to fix certain prices, etc. Minimal disruption. So how do you do the cutover? Essentially, hospital staff, people using it, we just go to bed one night and we switch the model. We just switch the API call, and the next day they woke up, and that's it. There's no difference. They felt that the accuracy was a bit better. It felt a bit more correct. They saw more variability in the cost, but that's about it. And of course it was faster, but they didn't quite notice it straight away. But there was no retraining required and everything. And this is so a lot of times we talk about models generating profit or saving costs, right? In this case, the way we implemented it saved costs because we didn't have to do expensive training and all that. And you know, a hospital, right? They have to be continuously. It's an essential service. It's an essential service that has to be continuously in production. So it's very difficult to take time out for training. Of course, we reduce costs and increase the frequency of updates. Our system is built for daily updates, and anecdotally, based on customer experience, we know that there were almost zero complaints. As we roll out more tanks of this, as we roll out more versions of this, I would go to the user acceptance testing. I would sit with them to see it. We got a lot of thanks from this, and that is very fulfilling, right? The hospital staff would tell us that, hey, you know, this works so much better. We get so much less complaints. We get so much less questions or pushback from patients who ask for estimates. And we know that this actually helps the hospital staff and the patient experience a lot. So key takeaways, building data products is a team effort. So you saw my overall architecture at the start. I only worked on the data preparation and machine learning stuff, maybe a bit of the model wrapper and deployment, but a lot of it, I had QAs to help, software engineers, DevOps, and a PM. So this is by no means all done by me. We have a team effort. And of course, be humble of the data. Don't assume anything. One big assumption I made was that combining all the data into a bigger data set would work better. But we know from here that this is not the case. So that's one key thing. And lastly, I know this has been said so many times that it's a cliche, but machine learning is really less than 20% of the effort. The methodology, how we frame the problem, how we implement it, how we execute, how we deploy it is far more important, has a far greater impact on the final outcome. That's it. Thank you for listening. I'll be sharing this on my website. You know, please go there if you like such material on data science and machine learning production. And I'll also be tweeting about such stuff on my Twitter handle, so you can follow me there. Thank you. That's it. And I'm open to any questions.
Yeah, thank you. So I have one question. Like when you mentioned a few slides back about customization, you know, here at institution level. So I was wondering how much work, like let's say you want to onboard a new hospital. I don't know if it was the case, if you actually needed to do that, but let's say if you needed to do that, how much work would it require to onboard a new hospital into your system?
So onboarding a new hospital, technically it's not difficult. So I'm trying to think through how we would do it now. We would provide them, hey, this is the schema that we expect your data to come in. They provide us the data in the right format. We would train the model and we would validate it, and we would tell them, hey, you know, okay, the accuracy is about this level. If you're okay with it, and then we deploy it. So the code base and the pipelines, everything is exactly the same. The only difference is we take in their data format in their scheme, in their data in the same format, and everything's exactly the same. Essentially, you could just take this, if all the hospitals provide the data in the same format, we would just take this and put it through the pipeline, and it would spit out a model deployment object, and we would deploy that.
Okay. Yeah, just wanted to remind that if you want to ask a question through slide, that there is a pinned message in YouTube chat. You can just click on the link and ask a question there. We also had a question in YouTube chat. It was in the very beginning about insurance. Like I think like I don't know how it happens in Singapore, but let's say in Germany, like when you have some sort of when you need to go to a hospital, usually insurance pays, so not a person out of their own pocket. And at what point insurance is involved into this procedure here? Like, are they the main customers here, or people still pay themselves?
I can't quite recall, but I would say that in Singapore, insurance is covered, but it depends on the coverage of the person. So different people have different levels of coverage. For example, one level of coverage is complete coverage, and that is very expensive. Another level of coverage is you have to pay 10% or a maximum of, I don't know, maybe $3,000 of your own pocket before the insurance pays. So I do recall that the hospital staff would take some of these estimates and run them by insurers to sort of get a letter of authorization. I don't think it's a letter of authorization, but a letter of some sort from the insurer that, we are going to cover this up to so much. But I don't think that even if the estimate is wrong, the insurers can decline to pay because it's part of the insurance coverage. So yeah, but I'm afraid I'm not quite familiar with that aspect.
Okay, so insurance is involved. It's not just this is not something you was exposed to. You were exposed to.
Yeah. So if insurance is involved, I recall now that there's a very interesting. So we do have insurance of the patient as a variable, and it's pretty interesting how this works. So one thing we found is that patients with higher levels of insurance actually get higher medical bills. So I'm not quite sure what the correlation is. It could be that people with higher levels of insurance are older, therefore their treatments are more expensive. Or it could be that when the doctors see that, hey, you have higher level of insurance, I'm going to give you the first class stuff, and they can make more money as well. I don't know.
Okay. Yeah. Well, I do not have any more questions, but let's wait for 10-20 minutes because there is this delay. So if you want to ask a question, so click on this link that is pinned, ask a question. And if we don't see any questions in 20-30 seconds, then
No problem. Yeah, I think everyone's tired after
yeah,
4 days or 4 hours of
4 hours,
conferencing, right?
yes.
Yeah. So it's expected.
I am, yes.
Yeah.
Not everyone probably stayed that long.
Yeah. And as I guess a reminder to everyone who's listening, we have 3 more days of conferences in the next 3 weeks
Oh, thank you.
on topics of career, machine learning in production, and processes.
Yes, exactly. So the next one will be about processes. Then it will be about career, and then the last one is about machine learning in production. Exactly.
Yeah.
And yeah, all the information is of course on our website. And there is a new question. Yeah. Is the patient data anonymized? How is privacy concern addressed?
Yes. So our model, doesn't use patient ID. So in that case, it's anonymized. And using patient ID is really a clear case of overfitting. So we don't use that. Nonetheless, things like demographics and gender do make a big difference in the prediction costs. So, yeah.
And the reason you don't use ID, because I assume there are cases when knowing the past history is useful, or not for this particular use case.
That's a good point. There are cases whereby knowing the past history is useful, but we don't use that. because we don't, in the first place, I think, so I can tell you for certain that in the first place, when they pass us the data here, the patient ID is hashed. And there's no way for us to track it. And we don't want that. We don't want that data in our system as well. It's a lot more compliance work. So therefore, what we do is we rely on the hospital staff when they enter the data. They sort of have to tell us what were the previous cases they have. That's all we. That's how we try to get around this.
Okay, makes sense. Thank you. Well, I guess that concludes our talk and the track for today. Thanks a lot for coming, for joining, not coming. So I should stop saying coming, right? Because
Yeah.
it's, well, yeah. Thanks a lot. That was nice, and I really liked your slide with like miscellaneous stuff. Like like these 3 bullet points. I think they're like, I should print and put it on my wall. Yeah, that's
Yeah, I think
great stuff.
I think people don't focus on that. Don't focus on it enough. The miscellaneous stuff, but that's what really matters. That what's make a big difference in terms of model performance in production, as in the impact that you have. So I don't know. I hope it's useful for the audience as well.
Yes, for me definitely. Thanks a lot, and thanks everyone for staying for 4 hours. I know it was difficult. Of course, everything will be like it's on YouTube, but then I'll cut the video and upload each video separately. And then from you, Eugene, I'll need slides.
I
I
have a link
guess.
for you.
Yeah. Okay. Cool.
Okay.
And then people already know how to find you. Your first name, last name.com, right? And
Yeah.
then all the information is there. Thanks a lot for joining, and have a great weekend.
Take care, everyone.